So, in the lectures so far, we have seen various ways to model both combinational and sequential circuits. So, if you recall, we talked about and also learnt how to model so called behavioral specifications of some digital system block, and also we learnt how to model some designs in a structured way, structured design. So, broadly speaking, designs can be categorized into behavioral and structural. And one thing, so far whatever results that we discussed, we showed they were based on simulation only. But in reality, whenever you are trying to design a hardware block, I mean either on FPGA or on ASIC, then you will have to use some kind of synthesis tool. Simulation can only be a first step to carry out initial verification of your design. But when you are doing synthesis, you may see that a lot means other problems are cropping up. There are some errors which are showing, which were not reflected during the simulation phase. So, in this lecture we shall be talking about some of the features of the Verilog languages that are meant to be used for synthesis. The other features which we have discussed in the class, but they are often not accepted by a synthesis tool. If you use those constructs, the synthesis tool will not be able to generate the final hardware circuit or the netlist. Okay. So, the title of today's talk is Synthesizable Verilog. So, whatever I had just talked about just now. So, the Verilog language provides you with a number of facilities and features, and these features are mostly supported by the simulation tool. For example, the simulation tool that we have been using as part of this course, the iVerilog, and of course, the waveform viewer GTK wave, they are all known to support most of the Verilog constructs that we have been discussing throughout the class, right. But as I had said, there are some language constructs which are not accepted by the synthesis tools. The subset of the language Verilog which are actually accepted by the synthesis tools are referred to as synthesizable Verilog subset. Now, in this lecture we shall be looking at some of the language features which are not supported and some of the recommended styles of modeling for synthesis of circuits, both combinational and sequential. So, talking about the synthesis rules for combinational logic, you recall what do you mean by a combinational logic? A combinational logic is a hardware circuit which does not have any kind of fan outs or storage devices built into it. So, the output of the circuit will only depend on the currently applied inputs. Well, of course, the circuit, the gates will have some delays, the output will be available just after the circuit delays. There is no notion of clock and other kind of synchronization that come in case of combinational circuits. So, you can say that the output of a combinational circuit at some point in time, let us say t, should depend only upon the inputs that I have applied at that time. Okay. Of course, there will be a delay of the circuit that we are not mentioning here. Well, so when you are trying to model combinational logic, there are some rules that need to be followed. First thing is that since you are talking about combinational logic, do not use means any kind of technology dependent modeling, means specifically some details about timings. See the timing detail using that hash command. So, whatever you give during simulation, that is just meant for carrying out the simulation and interpreting the waveforms that you are viewing after the process of simulation is over. But when you are synthesizing, your final delays will be dependent on the actual hardware. So, where you are mapping, it can be ASIC or FPGA. So, you do not have any control about the delay. You cannot say the delay is 1 or 2 or 3 nanosecond or picosecond. You cannot say that. That will be entirely depend on the hardware where you are finally going to map your design to. Okay. So, this kind of technology dependent modeling are not allowed when you are trying to synthesize combination circuits. Secondly, of course, in a combination circuit there are no feedback. So, your netlist or your circuit must not have any feedback. Feedback means some connection from the output of a circuit to the input of a circuit. Let us take an example. Suppose I have a circuit like this. There are other inputs. Suppose what I say is that this output line is connected to one of the inputs. This is what we mean by feedback. Well, feedback is not allowed in a combination circuit for obvious reasons, because when you feedback, your circuit may turn into a sequential circuit. Right. So, in this example, let us say we have applied a 1 here, we have applied a 0 here and a 1 and 1 here. So, now what will happen? What will be the behavior of the circuit? Let us suppose that initially the output of this NAND gate is 0. So, 0 is being fed back, this is 0, 0 and 1 NAND will be 1, 1 and 0 NOR will be 0, 0, 1 and 1 NAND gate. So, the output will be changing to 1, right. Now, when the output is changing to 1, this 1 will again be fed back. Now, the new input will be 1, 1 and 1 will be now 0, 0 and 0 will be now 1, 1, 1, 1 will be again 0. So, there will be something called oscillation in the output. It will continuously go from 0, 1 again to 0, again to 1, again to 0. So, the output will never stabilize. So, if your objective is to design a combinational circuit, you must avoid feedback connections like this. There must not be any kind of feedback in your netlist or circuit, right. And the third point I mentioned repeatedly earlier, that whenever you are having some kind of multi-way branching, so either using if else or using a case construct, where you are checking for some condition and then you are deciding on something, some assignments. So, here the output of the function whatever you are assigning to must be specified for all possible input cases. Like for instance, if you are checking for a condition which is a 2-bit variable, then you must specify what the output will be for all 4 combinations of those 2-bit variables, for 0 0, 0 1, 1 0 and also 1 1. So, we discussed earlier that if you forget to specify one of the input combinations, then the synthesis tool will be generating a latch for the output. So, even if you are trying to generate a sequential circuit, so whatever will get generated will be means actually you are trying to generate a combination circuit, but whatever will be generated, that will be a sequential circuit with a storage element. Okay. So, you must avoid this kind of incomplete specification in multi-way branching. Okay. So, means as I said, if you do not follow these rules, the circuit may become sequential. Okay, here are some styles that you need to follow for the synthesis of combination logic. Some of this we have already seen, some of this we have not talked about earlier. We shall just look at them through some examples. Like the possible styles may be, firstly we have seen several examples. So, you can instantiate the basic primitives of gates AND, OR, NAND, XOR and so on, and you can create a netlist like that. Secondly, you can use user defined primitive for combination circuit. You can define a truth table, right. Most of the synthesis tools support combinational UDPs, but you need to check there are some synthesis tools which will not accept any kind of UDPs at all, okay, even if it is a combination UDP with a truth table. Okay. So, that is mentioned, not all synthesis tools will support this feature. Then continuous assignment using assign statements. This of course, you can use for modeling combination logic, and functions are something which I have not talked about earlier. These functions are something where means you can use this continuous assignment statements in conjunction with the functions. We will see, and we will see that there are some advantages, or the code becomes much easier and more structured. Then of course, we can use the always block for modeling combination circuit. We have seen many examples here, behavioral statements, and just like functions, there is another thing called tasks. So, we can use tasks as well, but we cannot specify any kind of delays, and you can use a netlist of the modules created using one or more of these. You can combine, I mean any number of them, you can create some kind of interconnection of them by using instantiation. Let us look at these examples, some of these one by one. So, as a gate netlist, so we have seen many examples earlier. This is a very simple example. There are 5 parameters, these 4 are the inputs and y is the output, and this y1, this w1, w2, w3 are some intermediate wires. So, here we are specifying that there are 4 gates, OR, x1, x2 is the input, w1 is the output, this is second OR, XOR and a NAND. So, in this way you can create any kind of netlist. Now, the point to note is that here we are directly specifying the gate types, but the synthesis tool, when it is synthesizing, it will be generating the final hardware, right. So, the final hardware will be generated based on some target library. Let us say for example, the target library does not contain any exclusive OR gate. So, the XOR gate which you have specified here, they will have to be generated using different kinds of gates, maybe a combination of NAND gates or AND OR NOT gates and so on. So, during the synthesis process, whatever gates you have specified, there can be some changes as well, because you will have to use gates only from the target technology library, that is called. That means, the target gates which are supported by the hardware. So, during the process, the synthesis tool also carries out some kind of optimization. Okay. So, these are done here. So, when you are carrying out this mapping, some of the gate level minimization algorithms can be used. Okay. Next, continuous assignment is something which also we have seen through many examples. Here we can use an assign statement to assign some Boolean expression to a variable which is of type where. Now, this is a very simple example, a module which computes the carry output of a full adder. So, it is AB or BC or CA, right. So, here also we have not specified any gates, here we are specifying just the function. So, the synthesis tool again will take the functional specification as the input and will be trying to generate some gates or cells from the target technology library after some kind of minimization or optimization. Okay. This is what will be done if we use the assignment statement. Similarly, you can model combination circuits using procedural block assignment, where the event is not an edge triggered event. This is an example of a simple example of a 2-line to 1-line multiplexer, where in 0 and in 1 are the inputs, cell is the select line and f is the output. So, these 3 are the inputs and f is the output, which is also reg, because you are assigning f within a procedural block. So, here we are saying always whenever any of the inputs are changing, if the select line is 1, then in 1 is selected to f, otherwise in 0 is selected to f. So, the point to note is that when you are specifying a combinational logic like this, your activity list must contain all the inputs. In this case, the inputs are in 0, in 1 and cell. So, all the inputs of the behavior which are used in this procedural block must be included in the event control, because if you do not do it, the synthesis tool will assume that well those are not the inputs, but still you are using it. So, if the inputs are not specified, you do not know, you may have to use a latch to store the output f. So, a latch will often be inferred by the selection tool if you give incomplete input list specification. So, make sure that you give a complete input list specification in this always block. Okay. Now, let us see how functions work. We have not talked about functions earlier. See, function is very similar to a function in a high level language like C. In a language like C, you can have functions. Now in a function you can pass a number of variables through the parameters, but you can pass a single result through the name of the function. So, here also whenever you are using a function, it is intended to have a single output, a single bit output. So, it cannot have more than one outputs. This is a restriction of function in Verilog. So, let us say here we are trying to write a module for a full adder just using assign statement, but instead of directly writing down the expression, we are calling two functions sum and carry. These two functions we have written separately. Function, the syntax is like this: function followed by the name, sum is the name. Then I will have to specify a list of the inputs, and they have to be provided in the same order you are mentioning them here, A, B and carry in. So, A will be mapped to x, B will be mapped to y and C in will be mapped to z. And then here you are giving an assignment statement, where the left hand side is the name of the function and right hand side is any expression based on these input variables. This is the sum function. Similarly, this is the carry function. So, you can directly call these functions in the main full adder module. What is the advantage is that your module becomes easily understandable, it is much more well documented. So, instead of writing the expressions here, this module will become more clumsy, rather than if you write like this, it will be much clearer. So, as I said, so a function in Verilog will return a single value, here sum, here carry, and the value will be returned against this expression. Whenever you are writing an expression on the right hand side, so whatever is the calculated value of sum, that will be assigned to S. Similarly, for the carry function, the value will be assigned to C out. So, this makes the code more readable, as I said, and these are typically used with assign, as this example illustrates, and also I have shown that the input arguments must appear in the same order, okay, in the function and the place where you are calling them. Now, let us come to tasks. Well, a task is more general. Before going into the example, let us see what a task is. The first thing about task is that using task is like a function, but you can pass more than one output value to the calling program or the module. Like you see an example. And you see, for function you can use it only inside assign as I said, but a task can be used anywhere. Task can be used anywhere inside a Verilog function. You write a task and you can call it from some place. So, wherever you have defined the task, that will get substituted in the place where you are calling with proper argument passing. Okay. Let us take this example. So, this is again a full adder example. So, what you are saying, we are using the behavioral modeling, we are saying always at A or B or C in whenever the inputs change. Well, instead of writing the sum and carry expressions, we are calling a task. Now, f a is a task we have defined, f a within bracket the list of parameters s carry out a, b, c in. So, in this list of parameters, 3 of them are inputs and 2 of them are outputs. So, s and c out will be returned. Now, the way task is defined is like this: task, name and end task, and inside this you will have to specify the outputs and the inputs in the same order as they appear here. Like S and C out are the 2 outputs, you specify them, maybe the names will be different here, we call it them sum and carry. Then A, B, C in, they are the inputs. So, here you call them A, B, C. Now, in task you see you can also specify a delay, which you cannot in a function. So, sum expression, carry expression. So, this is how we can use a task in a function. Now, in our earlier examples which you have seen, we have not given any example that uses function or task, but if you want for larger designs you can use functions and tasks as well. Okay? Fine. Now, let us look at the difference between a function and a task. So, what are the main difference and where you can use a function and where you can use a task, right. So, let us see this table. So, a function, first thing is that so a function can call another function, but a function cannot call a task. So, you can have multiple functions and you can have nested calls. A function x can call a function y, y can call a function z, just like in a high level language we do. Okay. This is how function calls are made, but tasks are more general. So, a task can either call a function or it can call some other task. Now, in a function the concept of delay is not there. So, it is assumed that a function will execute in time 0, but in the task, in the example that I have shown, it also shows there that you can also include some delays. So, it can execute in non-zero simulation time, and a function just usually contains only combinational assignments, nothing else, but in a task it can be more general. You can contain delay like the example showed, you can contain some event triggering or some timing control statements as well. The function returns a single value, this is another thing, and a task it may return more than one value through output arguments. Like in the example that I showed earlier, there were 2 output arguments sum and carry. Now, another kind of port declaration is there which I have deliberately not talked about. I shall take some examples later. These are some kind of bidirectional inputs, in out. Well, in out means you can use that variable as an input and also as an output. Okay? But when you map it to the hardware, sometimes some problems are created for in out type variables. That is why in the designs that I have shown, I have avoided in out. Okay? Fine. And another thing is that a function must have at least one input argument, but there is no such restriction in task. It can have 0 or more arguments, and the arguments can be of type either input or output or in out. Now, these are some of the constructs which you must avoid when your objective is to carry out combinational circuit synthesis. Like we should not give this edge dependent event control, like you must not give means always at pause edge clock or neg edge clock. No kind of pause edge or neg edge kind of event control should be there in a combinational circuit description. Then second thing I already mentioned, there must not be any feedback loops. So, when you specify netlists using instantiations, make sure that you do not include any feedback loops. Third thing is that you can have procedural assignment or continuous assignment, but there must not be any delay specification or event control, because in synthesis those are not considered. Similarly, you can have a loop with timing, there can be some delay specified, such delays are not allowed. Then data dependent loops. Data dependent loop means some kind of a loop where the number of times you are going to loop, it depends on a variable. That kind of thing is not allowed. The number of times you are looping must be a constant. So, if it is a constant, suppose 3, I specify I want to execute a for loop 3 times, then the synthesis tool will make 3 copies of whatever is the body of the loop. It will make 3 copies of the circuit and it will create a combinational circuit like that. There will be 3 levels, which corresponds to the 3 iterations of the loop, right. Sequential user defined primitives like state table are not permitted by synthesis tools, and there are some other miscellaneous constructs which I have not discussed deliberately, like fork join. These are used to specify concurrency. Wait, well, wait is used sometimes to make a statement wait for certain time before it gets activated, and of course, disable, you can disable some signals or commands. So, to summarize, the synthesizable Verilog constructs, the constructs that you must use when your objective is to synthesize the design into some hardware, they are as follows. Module and module, of course, well, you are allowed to carry out instantiation, you can use always constructs, assign statements, built in get primitives like AND, OR, NOT, XOR, NAND, NOT, these you can use. But for user defined primitives, you can possibly use only combination specification, but still you will have to check with the synthesis tool you are using that whether the tool supports combinational UDP or not. Okay. Parameters you can use, functions and tasks as I mentioned just some time back can be used. For loop is usually supported by all synthesis tools, the other kind of loops may not be supported. So, again you will have to specifically check whether the other kind of loops like while or repeat, they are supported or not. Okay. Regarding operators, almost all the operators are supported, barring a couple of them, a very few. Blocking and non-blocking assignments are supported, and multi-way branching using if, else, case, case x, case z. So, you can use bits, and with respect to vectors, the part selection, you can select some segments from a vector, those are supported. Okay. So, if you stick to these rules, that means you will not be using anything outside this, then it is often guaranteed that whatever module that you write, that can be synthesized into a hardware by the synthesis tool. Okay. And there are a few things which are not synthesizable definitely, like initial construct, it is meant only to be used in the test benches. Delay specification using the hash command. So, you cannot use delays in synthesizable code. Time, no concept of time in synthesizable code. Real data type is often not supported, only bits and integers they are supported. And the operators, this triple equal and not equal to, these two are not supported. Fork join, force release, and as I said, in loop control you cannot loop variable number of times. So, variables in loop control are typically not supported. So, with this we come to the end of this lecture. So, in this lecture we try to give you just an idea that what are the constructs in Verilog that you have learned so far, which are useful for synthesis, and what are the constructs which are best avoided, because most of the synthesis tools do not support that. Now, in the next lecture we shall be continuing with our discussion. We shall be talking about some recommended practices, some do's and don'ts. You see, Verilog may be supporting a few things. So, the synthesis tool may be supporting many things, but if you go to an industry who is specialized or who specializes in design, they will give you some guidelines. The designer will have to stick to those guidelines whenever they are designing any circuit using some language like Verilog, because if they do that, then the codes will be well documented, they can be reused and they can be maintainable. Okay. Thank you.